Acceptance testing using vibration analysis, ensuring equipment reliability through precise vibration monitoring. Introduction to acceptance testing, importance of acceptance testing in industrial plants, acceptance testing for new and overhauled equipment, role of vibration analysis in acceptance testing, ISO standard supporting acceptance testing, setting vibration limits for acceptance, acceptance test planning and procedures, baseline measurements and data comparison, common reasons for acceptance test failure, key takeaways and engineering best practices. Acceptance testing is a critical engineering practice used to verify that rotating machinery meets defined performance and quality requirements before it is formally accepted into service. In the context of vibration analysis, acceptance testing focuses on identifying mechanical, electrical, and structural issues that may not be visible through visual inspection alone. Vibration data provides direct insight into the dynamic behavior of machines such as motors, pumps, fans, compressors, and gearboxes, making it one of the most effective condition-based acceptance tools available to engineers. By measuring vibration amplitudes, frequencies, and phase relationships, engineers can confirm that a machine has been manufactured, assembled, transported, installed, and commissioned correctly. From a plant reliability perspective, acceptance testing serves as the first line of defense against premature equipment failures. Many chronic vibration problems originate at the supplier or repair shop stage, including rotor imbalance, misalignment, soft foot, bearing damage, or resonance conditions. If these issues are not detected before startup, they can lead to repeated breakdowns, increased maintenance costs, safety risks, and reduced equipment life. Acceptance testing ensures that these defects are identified and corrected before the equipment becomes operational, when corrective actions are least expensive and least disruptive. Another important aspect of acceptance testing is its contractual and procedural role. When acceptance criteria are defined in purchase orders or repair contracts, they create a clear, objective basis for accepting or rejecting equipment. This protects the plant owner by ensuring that suppliers and contractors are held accountable for meeting agreed technical standards. Acceptance testing also establishes a documented vibration baseline, which becomes an essential reference for future condition monitoring and fault diagnosis throughout the machine's lifecycle. In this way, acceptance testing using vibration analysis is not merely a quality check, but a foundational element of a comprehensive reliability and asset management strategy. The importance of acceptance testing in an industrial plant cannot be overstated, particularly in facilities that rely heavily on rotating machinery for production, utilities, or safety-critical operations. Acceptance testing directly supports plant reliability by ensuring that equipment enters service in the best possible condition. Statistics across multiple industries consistently show that a large percentage of machinery failures occur shortly after startup. These early life failures are often the result of latent defects introduced during manufacturing, repair, or installation, all of which can be detected through proper vibration-based acceptance testing. From an operational standpoint, acceptance testing helps prevent unplanned downtime and production losses. When defective equipment is commissioned without testing, vibration-related issues such as imbalance, looseness, or resonance may only become apparent once the machine is under load. At that stage, corrective actions often require shutdowns, rework, or even equipment replacement. By identifying these problems before final acceptance, plants can avoid costly disruptions and maintain stable, predictable operations. Acceptance testing also plays a vital role in safety and risk management. Excessive vibration can lead to fatigue failures, structural damage, and in extreme cases, catastrophic equipment breakdowns that endanger personnel. By enforcing vibration limits and verifying compliance before startup, plants significantly reduce the likelihood of such events. Additionally, acceptance testing supports long-term maintenance optimization. Machines that start their service life in good condition typically require fewer corrective maintenance interventions and respond better to predictive maintenance programs. Overall, acceptance testing is a proactive engineering practice that aligns technical integrity, operational reliability, safety, and cost control into a single, structured process. Acceptance testing should be applied consistently to both new equipment and equipment that has been repaired or overhauled by external contractors. Although new machinery is often assumed to be defect-free, experience shows that manufacturing tolerances, assembly errors, transportation damage, and improper factory balancing can all result in vibration problems. Acceptance testing verifies that the new machine meets the specified vibration limits under defined operating conditions before ownership is formally transferred to the plant. For overhauled or repaired equipment, acceptance testing is even more critical. Repair processes such as rotor balancing, bearing replacement, shaft repairs, and motor rewinding can introduce new faults if not executed correctly. Acceptance testing ensures that the repair work has successfully corrected the original problem and has not introduced additional issues. In many cases, repaired machines are returned to service without thorough verification, leading to repeated failures and disputes between plant owners and service providers. A key engineering principle is that acceptance criteria for overhauled equipment should be clearly defined and communicated before work begins. These criteria should include vibration limits, measurement locations, operating conditions, and test procedures. Where possible, acceptance limits for overhauled machines should be comparable to those applied to new equipment, provided the foundation and installation conditions are sound. By applying the same rigorous vibration-based acceptance testing to both new and overhauled machinery, plants establish consistency, accountability, and confidence in the mechanical integrity of their assets. Vibration analysis is the primary diagnostic tool used in acceptance testing because it directly reflects the dynamic forces acting within rotating machinery. Unlike static inspections or basic functional tests, vibration measurements capture the real operating behavior of components such as rotors, bearings, couplings, gears, and foundations. By analyzing vibration amplitude, frequency content, and phase relationships, engineers can identify specific fault conditions and assess overall machine health. In acceptance testing, vibration analysis is typically performed under controlled and repeatable conditions. Measurements are taken at defined locations and directions, such as horizontal, vertical, and axial points on bearing housings. Frequency domain analysis allows engineers to distinguish between different fault sources, such as imbalance at running speed, misalignment at harmonics of running speed, bearing defects at characteristic defect frequencies, and electrical issues at line frequency components. Phase analysis further supports fault confirmation by revealing the relative motion between machine components. Another key advantage of vibration analysis is its ability to detect resonance conditions. Through run-up, coast-down, and bump testing, engineers can identify natural frequencies of the machine, foundation, or connected piping. Ensuring adequate separation margins between operating speeds and natural frequencies is a fundamental acceptance requirement. Overall, vibration analysis provides objective, quantitative evidence that a machine meets acceptance criteria, making it an indispensable tool for engineering-grade acceptance testing programs. International Organization for Standardization, ISO, standards provide essential guidance for establishing acceptance testing criteria based on vibration and balance requirements. These standards offer a common technical language that can be referenced in purchase orders, repair contracts, and internal engineering specifications. By aligning acceptance testing practices with ISO standards, plants ensure that their requirements are technically sound, widely recognized, and defensible. One of the most widely used standards is ISO 1940, which defines balance quality requirements for rigid rotors. This standard specifies permissible residual imbalance values based on rotor mass, operating speed, and balance quality grade. ISO 1940 is particularly important for acceptance testing of motors, fans, and other rotating components that have undergone balancing during manufacture or repair. Another key standard is ISO 14694, which provides vibration and balance limits specifically for fans used in industrial applications. In addition, standards such as ISO 10816 and ISO 20816 address the evaluation of machine vibration by defining measurement methods, vibration severity zones, and general acceptance guidelines. While these standards may not always provide machine-specific limits, they serve as a valuable starting point for developing plant-specific acceptance criteria. Understanding and applying relevant ISO standards ensures that acceptance testing is based on proven engineering principles rather than subjective judgment. Setting appropriate vibration limits is a central element of acceptance testing and requires careful engineering judgment. Vibration limits define the maximum allowable vibration levels that a machine may exhibit and still be considered acceptable. These limits are typically based on machine type, size, operating speed, foundation stiffness, and application criticality. ISO standards provide general guidance, but plant-specific experience and risk tolerance often play a significant role in final limit selection. In practice, vibration limits may be specified as overall vibration velocity, displacement, or acceleration, as well as band-limited or order-based limits. Band alarms are commonly used to target specific fault mechanisms, such as imbalance, misalignment, vane pass frequencies, or gear mesh frequencies. Acceptance limits are usually more stringent than alarm limits used for in-service condition monitoring, reflecting the expectation that new or overhauled machines should be in near-optimal condition. It is also important to define measurement locations and directions clearly when setting vibration limits. Consistency in measurement practices ensures that results are repeatable and comparable. By establishing well-defined, technically justified vibration limits, acceptance testing becomes a clear pass/fail process that supports objective decision-making and supplier accountability. A structured acceptance test plan is essential to ensure that vibration-based acceptance testing is carried out consistently and in accordance with specifications. The test plan should define what measurements will be taken, where they will be taken, under what operating conditions, and by whom. It should also specify the instrumentation, sensors, and data collection settings to be used, ensuring repeatability and data quality. Typical acceptance test plans include requirements for run-in periods, load conditions, temperature stabilization, and safety precautions. They may also define whether testing is to be conducted at the supplier's facility, at the repair shop, or at the plant site after installation. Clear procedures reduce ambiguity and prevent disputes by ensuring that all parties understand the acceptance requirements in advance. Following a documented test plan also supports traceability and continuous improvement. Test results can be reviewed, audited, and compared against historical data to refine acceptance criteria over time. In this way, acceptance test planning is not just an administrative task, but a core engineering activity that underpins the credibility and effectiveness of the acceptance testing process. Baseline vibration measurements are a key output of acceptance testing and serve as a reference point for the entire operational life of the machine. These measurements are typically collected during the final acceptance test, either at the supplier's facility or at the plant site after installation and startup. Baseline data should include overall vibration levels, spectral data, and phase measurements where applicable. The value of baseline data lies in its use for future comparison. As the machine ages, changes in vibration behavior can be compared against the baseline to identify developing faults and assess their severity. Without a reliable baseline, it becomes much more difficult to distinguish between normal machine behavior and abnormal conditions. Baseline measurements also support root cause analysis if problems arise shortly after commissioning. By comparing startup data with acceptance test data, engineers can determine whether a fault was present before installation, introduced during installation, or developed during early operation. This makes baseline data an essential component of both acceptance testing and long-term condition monitoring programs. Acceptance testing may result in rejection of equipment when vibration levels exceed specified limits or when abnormal vibration characteristics are identified. Common reasons for acceptance test failure include rotor imbalance, misalignment, mechanical looseness, bearing defects, electrical issues, and resonance conditions. Each of these faults produces distinct vibration signatures that can be identified through proper analysis. Installation-related issues are also a frequent cause of acceptance failure. Soft foot, improper grouting, inadequate foundation stiffness, and piping strain can significantly increase vibration levels even if the machine itself is in good condition. Acceptance testing helps distinguish between machine-related and installation-related problems, allowing corrective actions to be targeted effectively. Importantly, acceptance test failure should not be viewed as a negative outcome, but as a success of the testing process. Detecting and correcting problems before final acceptance prevents far more serious consequences later. A robust acceptance testing program ensures that only equipment meeting defined engineering standards is allowed into service. Acceptance testing using vibration analysis is a proven engineering practice that delivers significant benefits in reliability, safety, and lifecycle cost control. By understanding the importance of acceptance testing, engineers and plant personnel can ensure that machinery enters service in optimal condition. Applying acceptance testing consistently to new and overhauled equipment establishes accountability and reduces the risk of early life failures. The effective use of ISO standards provides a strong technical foundation for setting vibration and balance limits, while structured test plans ensure consistency and repeatability. Baseline measurements captured during acceptance testing support long-term condition monitoring and informed maintenance decisions. Ultimately, acceptance testing should be viewed not as an optional activity, but as an integral part of professional engineering practice in modern industrial facilities. By following these best practices, organizations can protect their investments, improve equipment reliability, and foster a culture of technical excellence grounded in objective, data-driven decision-making.